You go to Skellig and just do the whole route. You go 77, you got like toil.
Okay, so what are we doing? I gotta go scroll down. Okay, we were looking at Euler equations. This is our first version of a non-constant coefficient differential equation because you have a t squared in front of this and a t in front of this, but they're a very particular form. It's equidimensional, which means that you have the same power on the t. The power on the t is the same as the order of the derivative. And so when it's of this form, turns out that the solution form that will have the property of making every term on the left-hand side equal to the same kind of terms. So they're all going to be t raised to the r terms, is if you plug in something like ct to the r, which is not the same as ce to the rt. So this was like when you had constant. So the green one right here is when you had constant coefficients. That was going to get you all the terms to have like e to the rt. But you need, because of the t squared and the t, we propose a solution form of cet to the r, and that reduces the power on the t for each order that's compensated by the t squared and the t, and then that's why all the terms end up being t to the r. And you can force this solution form to satisfy the differential equation for all t's, and you can also ensure that it's non-trivial solution. So C, capital C is 0. The only condition would be to make this inside this parentheses equal to 0. It looks a little different than the characteristic equation because our equation is different, the solution form is different, but it behaves in the same kind of way the characteristic equation behaves, in that the roots of this are going to be the r's that go into your solution. And in the solution form is ct to the r instead of e to the rt. And this is like our characteristic equation for this problem, but it's got a different name. It's called initial equation. And then, of course, it's the quadratic equation in R. So you'll have all the three cases. So the first case is the distinct real roots, which you just write one as t to the one of the r's and then t to the other r. So if you got two distinct roots. The other, so that's that. And the other case was if you had two complex roots, those would come in conjugate pairs. And using Euler's formula from before, the issue is that our solution form is not in a complex exponential immediately. You'll have to like force it to be a complex exponential, or you can make anything become an exponential by taking the ln and exponentiating it. And so we did that and used the results we had before and got this summary. So the idea is that if you have conjugate pairs of complex roots, you have a real and imaginary part. And the pattern is always going to look like, we did a specific example here where it was -1 plus or minus 2i, and saw that the spots where the alpha and the beta go were here and here and here. That will always be true in general. And so the summary for the complex case is if you have a complex conjugate roots, the real part goes here, the imaginary parts go here, and there's an ln of t that's inside the argument for sine and cosines. So it's different than the constant coefficient case, but the idea is that it's using this different solution form. Of course, the differential equation is different, and then you are using Euler's formula as well and behind the scenes. You don't have to know how to derive this solution form, but at least you know where it comes from. It's from Euler's formula. So the last case is the repeated roots case. So if you have a repeated root, for sure one of them will be t to the r. The question is, if you had two distinct roots, then one of them would be t to the r, and the other one would also be t to the r, and the r's would be the two distinct roots. But if you only had one repeated root, then only one of them will be like this. And if you remember from the past, when we had constant coefficient, so right here for so not Euler, but constant coefficient. ODE. We got our solution for one of them was like e to the RT. I mean, I guess it's multiplied by some constant, but that's arbitrary. But the main part of the solution is e to the RT. And then we said that the second solution, homogeneous solution, was not just e to the RT, but what? If you had repeated roots in the past, it was t, e to the RT. So there was this extra factor of t that got multiplied in the past. So for Euler equation, we're going to do something like that as well, but we're going to actually multiply by ln of t instead. So that's different than what we had before, but we'll take t to the r and then you copy that and then multiply by ln of t. Last time it was we took e to the RT and then multiplied by t. I actually haven't justified these two. Well, I mean, obviously, I just said this right now, but in the past, this right here, I also said that I'd have to go back and justify this. Why do you multiply the second homogeneous? So the first one makes sense because this is what you get out of forcing the solution form to satisfy the differential equation, and you find r that satisfies the characteristic equation. You have a repeated root, so you only have one root. And so, one of them should be this, but why is the other one got multiplied by t? This one, it's the same idea. Why is the other one multiplied by ln of t? But I'll tell you that's how it is. But in a moment, we'll actually justify this using reduction of order. So the punchline is that if you have a second order Euler equation like this, and you get repeated roots, one of them will be t to the r. The other solution will be t to the r ln of t. So let's just do an example. Again, the initial equation is slightly different from our Euler equation. Let's say that we have our initial equation is a, well, it's going to be 1 because it's a is equal to 1 on this one. So it'd be r minus r1 minus r is plus 1 is equal to 0. And then you'll combine terms, so you'll get r squared out of this. Minus r is minus 2r plus 1 is equal to 0. And this right here can factor into r minus 1 squared is equal to 0. So therefore you get r is equal to 1. But it's a double. So one of the solutions is what we expect, but the other one's going to have to be multiplied by ln of t. So that's it. So the solution would just be equal to t, well, c1, t to the 1. The other one would be c2, t to the 1, but then ln of t multiplied 2. So you have to remember to multiply by this because this is a repeated root, and then you'll have your final answer. Okay, so that's repeated roots for Euler equations. So we have those three cases, slightly different than the constant coefficient differential equation case, but similar ideas. The initial equation takes the place of the characteristic equation. Your solution form is not e to the RT, but t to the r. So now we're going to move into justifying why we multiply by t for the second homogeneous solution whenever we had repeated roots. So let's go back to when we had constant coefficient differential equations. Of course, we already know how to do this one without using reduction of order, but I want to justify why we ended up multiplying by t. So you can do the characteristic equation. This is designed so that you will get a double root. And you're going to get your homogeneous solution. Well, this equation is homogeneous, so you just have the homogeneous solution is going to equal, remember, this is constant coefficient differential equations. So the solution form was e to the RT, right? So it's going to be therefore C1 e to the, one of them will be 3t plus C2 t e to the 3t. We know this from before, but the question is, why did we multiply by t here? We are comfortable with certainly one of the homogeneous solutions, so I'll label this as x1. One of our homogeneous solution is e to the 3t, but why is the second one t e to the 3t? And I never justified that. So the first one makes sense because we know the solution form is c e to the rt, and all the r's that satisfy the characteristic equation are going to force that solution to satisfy the differential equation. But then you only have one because it's a repeated. So the other one is just a copy of it times t. So we're going to say that we're comfortable with e to the 3t. We're uncomfortable with t e to the 3t. So we're not going to justify why the first one is this, because that one's fine. But why is the second one like this? So what we're going to do is we're going to say that, let's suppose we don't know that we needed to multiply by t for the second homogeneous. So only we had was the first one. So we know we had only one root. It's repeated. So we just know e to the 3t because it's double root. But one of the roots, it's just one root, but it's double. One of them is e to the 3t. And let's pretend like we don't know what the second one is. So what I'm going to do is I'm going to propose that our general solution, x of t, is going to be some unknown function v of t times our one homogeneous solution that we do know for sure is good. Okay, so, and that of course is a function of t. So I'll just say x1, technically this is our x2. The book likes to label the homogeneous solutions as x1 and x2. The question is, given that we know that one of them is x1, how can I justify that the second one has to have been multiplied by t? What I'm going to say is my general solution is going to be some function v of t times x1 of t, some function v of t that I'm going to find that will force this differential equation to be satisfied. So right now, I'm just leaving this v of t as general. I'm not saying x of t is anything. I'm saying like I'm going to build it off of the first homogeneous solution. So it turns out to be a product of the first solution times some v of t, and then the goal is, so we already know what the x1 is. X1 is this e to the 3t. So it'll be v of t e to the 3t. And the goal is, how can I force this to satisfy the differential equation? So we want to find this. Okay, so what I'm going to do is, right, we already know that x1 is, so I'm just using the fact that x1 is equal to the one homogeneous solution we know. You could, say c to the 3, c1 times e to the 3t, but it really doesn't matter. Your v of t will have this additional arbitrary constant, and you could just pick one is fine. So, one with c equal to 1 is fine. So we're going to plug this into the differential equation, but of course there's a second derivative and first derivative, so we're going to have to take the derivatives of these. But you have to do the product rule because we're going to assume v of t is not some constant, but some function of t that is to be determined. And we're going to find what it is to force this thing to satisfy the differential equation. So we're going to assume in general, it's not going to be a constant. It could be a function of t. So that means you have function of t times e to the 3t. So two functions of t. So you're going to have x prime. The derivative is going to become, take the derivative of the first times the copy the second, plus you take the derivative of the second. So there's going to be a 3 that pops out of e to the 3t. And then you're going to do x double prime. You'll get v double prime e to the 3t. This is a double prime. You'll get another 3. This one's going to have a prime. So overall, you're going to have, I'm combining terms here, but you'll get 2 that add up to become 6v prime e to the t. And then the last is going to be the 9v e to the 3t. So those are your derivatives. And then we're going to plug this in to this differential equation. And so you have the second order derivative. It's this one. And then you're going to have minus the 6 times the first order derivative, which is this one, plus the 9 times this proposed solution is going to be v times e to the 3t. And this has to equal 0. So just keep in mind that our v's, all the v's, I'll just write it here. All the v's are functions of t. I'm just not writing the parentheses of t for each of these because that would be a lot of writing. So we need to find, right? The goal is to find this. Just say the goal is to find this v of t that will get multiplied to the e to the 3t and would satisfy, or we're trying to find the v of t that would force this solution to satisfy this differential equation. So we have this, and it's an equation in v. We want to just like solve for the v that would satisfy. I mean, it's an equation, it's a differential equation in v because the v's got the primes on them. But it turns out that we can simplify this if we just look at let's underline all the v terms. So I'm going to just underline all the terms that have v in it. So this is 9v, 3v, 9v. So there's 3 of those. Now, if you distribute this 6 to this 3, you get negative 18 ve to the 3t. But the 9 plus a 9 are going to be also 18, but positive. So these will all cancel each other, actually. And that'll always be true. All the v terms will cancel each other. The book describes that this will always happen for a general, they leave, they don't use specific numbers. They just leave A, B, C in front of these and then show in general that all your v terms after this process will cancel. And it comes from the fact that you're building the solution with x1 and x1 is a homogeneous solution. So from that, it will always result in the v terms canceling. The v prime terms are here and here. And these will generally not cancel, but in this problem, they end up canceling because the negative 6 multiplied distributed to this and the 6 are positive and negative, so those will cancel. So that doesn't happen all the time, but it does in this case. Of course, if you don't get your v's to cancel, so all the purple underlined terms to cancel, they should cancel in general, which you can prove, or the book proves. The reason you might find that you're not getting them to cancel is if you did the product rule wrong, or if you took these derivatives wrong, x prime and x double prime. So that's a catch that like you might have done this right here wrong, then you're not going to get it to cancel. But once all these terms are eliminated, all we have is that you have v double prime e to the 3t is equal to 0. You could just divide everything by e to the 3t, because e to the 3t is never 0, so you can divide by that, and so you'll just get v prime is equal to 0. This is a very easy differential equation in v. If you integrate this, then you'll get v prime is equal to what? Is not t. If you take 0 and integrate it, it's some constant. Good. We're going to call that C1. I don't know if that's what you said. I couldn't hear, but it's just a constant. Now let's integrate this again. And if you integrate this again, you'll get not constant to an exponent. C1t. That's not it though. Plus C, plus C2, we'll call it C2. So there's always another integration that comes every single time you integrate. So that's why, one integration gives you one of them, and then another integration will give you this other C2, right? So we found V. This was the goal, was to find V. And that's why we needed to take the antiderivative twice, because this equation is just a V double prime is equal to 0. So we're just taking integrate and integrate. We need to integrate twice to get to the V that we want. But hey, we already said that our solution form, the V that will force this to satisfy the differential equation is going to be, so I would say that it was v times the x1. Both of these are functions of t. But we found that the v is equal to c1t times c2t, c1t times c2. And then our x1 was e to the 3t. And if you multiply this out, you get c1t e to the 3t plus c2 e to the 3t. So we made no, we didn't just say that our second solution had homogeneous. So if you notice, this is our first homogeneous solution. Don't worry about the C1s and C2 looks like they flipped, but those are just arbitrary constants, so it's okay if they're flipped. I could have easily just wrote this one first and then wrote C1 multiplied to it, and then this one second and wrote C2 to it. The idea is that you get this T to show up for your second homogeneous solution without making any assumptions of what the second homogeneous solution looks like. We're just saying we know we're comfortable with our first homogeneous solution being e to the 3t. Why don't we just say, I don't know what our general solution is, but it's going to be some function of t times our one homogeneous solution we're comfortable with. And then let's plug this in and find the v of t that'll force this thing to satisfy the differential equation. And we end up getting that v must have been this, multiply it out, and it's clear that that would have meant that the second homogeneous solution was t e to the 3t. We also get two arbitrary constants, which we expect because it's going to be second order equation. So that justifies using reduction of order, given one homogeneous solution that we know for sure is going to satisfy this differential equation, how to systematically get the other homogeneous solution. And so you don't have to take my word for granted. You could check this. This is the process that does it formally. So for Euler equations, we had something similar happen. This is an Euler equation because it's t squared and a t term and a non-t term. So you'll do the initial equation, r. This is 7r plus 16. And this multiplies out to r squared minus 18r minus 8r plus 16. And then this factors to r minus 4 squared is equal to 0. So you get that you got another double root here. You get r is equal to 4, the double root. And we already know from what we just said before that the solution for this homogeneous equation is going to be, it's a different solution form from the constant coefficient case. It's going to be, one of them is going to be C1 times what? T, good. T to the 4th, not e to the, so that's a common mistake. So just make sure that the solution form is different, right? We derive the initial equation using this kind of solution form. And the other one is C2, t to the 4th. And then we multiply by ln of t, which was really weird because it wasn't the t that we had said before. It was this ln of t, which we had up here. So why in the world is this ln of t here? We're going to show that using reduction of order. So this is the only time where we've multiplied by something that's not actually t. We're used to multiplying by t, but so the question is, we know one of the homogeneous solution is t to the 4 for sure. That one we're comfortable with. But why is the other one, this is our x2 homogeneous solution, why is that one got a multiplication by ln of t? So that's the question. So what we're going to do is the same process we did before. We're going to say that our x1, our homogeneous solution that we know is good, is t to the 4th. Why don't we build a general solution? So we'll propose x of t is built off of v of t times the x1, which is going to be v times e, not e, t to the 4th. Okay, And we're gonna try to plug this in and find the v as a function of t that will force this to satisfy the differential equation. So you're gonna have to compute a second derivative and a first derivative. So we're just gonna do x prime. This is gonna be 4c1 t to 3. Oh, no, sorry. I'm not taking the derivative of, I'm taking the derivative of this. You got to do the product rule still. I'll just say x prime is equal to v prime. V prime times t to the 4 plus v times the, so we'll just pull the 3 in the front, a 4 in the front, and so 4vt cubed. That's just using the product rule. And then we're going to also have the derivative of this, which is going to be v double prime t to the 4. There's going to be a 3v prime t to the 4. There's going to be a 4v prime t to the t to 3. Okay, so those combine, and so you're going to have a 4 and a 4. So it's going to become 8. I'm just combining terms. And then the last one's going to be 4, but then the 3 comes down, so it's 4 times 3 is 12, and then goes down, so it's going to be t squared. Okay, you can confirm this if it's hard for you to see this immediately right now. It is just taking the derivative. So we're going to plug this in. You got your, well, I got to be careful. There's a t squared, so I'll have to write that in. Multiplied by x double prime, which is all of this. And close that. Minus 7 times t times our x prime, which is all this. Plus 16 times our v times t to the 4. So this is our actual x. Okay, I'll just make it black. Okay, and this has to equal 0. Okay, let's underline all the v terms. This is a v term. This is a v term. This is a v prime. This is a v term. So there's 3 of those. Let's look at if they should cancel, right? So you have, okay, this t squared distributes to this t squared. That becomes a t to the 4. So this is a 12 and a 16 v t to the 4. Those will combine. This is a t, right? By the way, this is the t. So 12 plus 16 is 28. And then negative 7 times 4 is negative 28. This is a t cubed and a t, so at least they're all going to be t to the 4, so we're good. These will all cancel each other when they distribute out. The v prime terms, let's underline them just like we did last time, but I'm going to note that they don't appear to cancel, right? Because you have t squared times 8v prime, so this will be overall a t to the 5, but it'd be 8 with a v prime. This will be also t to the 5 because t to the t times t to the 4, but t to the 5, v prime, but it's a minus 7, so they don't cancel. And that's fine because in general, only the v terms can be shown to always cancel, and given that your x1 is a homogeneous solution. So we're left with the v double prime term here. There's only one of those. It's going to be t squared times t to the 4th. So it's going to be v double prime t to the 6. You have an 8 and a minus 7. So it's going to be plus v prime. Just 1. And then there's going to be a squared and a cubed. So it's t to the 5. And this is equal to 0. So we have an equation in V. It's a differential equation in V, a second order equation in V. And if you stare at this, it looks like we have an equation that we technically don't know how to solve because this is a non-constant coefficient differential equation. So maybe I make it clear by putting the t squared. Okay, so I'll write it with the t's in the front so that you can see that this is the same thing as this. So I'll just delete this. Right? All I did was I moved the t term in the front. So if you imagine these v's are like our x's, this is not an Euler equation because this is t to the 6th and this is t to the 5. So it doesn't have the same dimensions. So t squared has to be, this 6 had to be a squared and this 5 would have had to be a, I guess you could divide everything by t to the 4. But let's solve this using, this is where the name reduction of order comes. There's a v double prime and a v prime. What we're going to do is we're going to let w become v prime. If you let w become v prime, that means that the equation can be rewritten in terms of w if we're replacing v prime as w. If w is v prime, then what is v double prime? W prime plus t to the 5. And this is just w. So by doing this replacement, we reduce the equation by 1 order. So instead of a second order equation in v, we now have a first order differential equation in w. And we actually, even though we spent a lot of time doing second order equations, we actually are, we have more methods for solving second order equations, first order equations. So what we'll do here is we'll just solve for, so we'll just say t to the 6th w prime is equal to negative t to the 5 w. Just moving this to the other side. I'm going to do separation of variables. So you could just divide both sides by, I guess I'll just divide both sides by w, by t to the 5. So it'll just become t w prime is equal to negative w. That's after you divide everything by t to the 5, or t to the 5, yeah. And we're okay with dividing by that t to the 5 because I'm looking at only when t is greater than 0. So we're not dividing by 0. And then you have, I'll just write the w prime is just really dw over dt is equal to negative w. And you can divide both sides by t, divide both sides by w, so you get dw over w is equal to, I'm going to multiply by dt, so the negative dt over t. This is separating, so I'm just doing a lot in one step, but I'm dividing both sides by w, dividing both sides by t, and then multiplying by dt. And that'll separate this. And so you'll get, now that it's separated, you just take the integral of both sides. So you'll get, this side is ln of absolute value of w equals negative ln of absolute value of t. I'm not going to write the absolute value of t, I'll just write ln of t because we're only looking for t greater than 0. So we don't have to write absolute value. This is already going to be greater than 0. And then there's technically an integration constant from both sides that I'm going to consolidate and call it C1 on this side. And then we're just solving for w. I mean, we're solving for v, but we're going to first solve for w from this, and then we'll take the antiderivative of it to get v, because w is v prime. So just exponentiate. So we'll just say this is the same as, if I exponentiate this, it's going to become absolute value of w is equal to e negative ln of t plus c1. Okay. And then what I'll do is a couple of things. I'm going to split this out as we usually do. I'm going to move the negative up here. So I'm going to say this negative could be put as an exponent on top of this ln. That's a log property. So we have now, and then I'll drop the absolute value. So I'm doing a bunch. So it's going to be plus or minus after I drop the absolute value. I'm going to split this out and just say e to the c1 times e to the ln of t to the minus 1. Then the -1 comes from the fact that I pulled the negative sign that's in front. And there's like a -1 in front of this ln up here. I like to do that because then the e's and the ln's can cancel each other because they're inverses of each other. So then we have, so the other thing I'll say is this right here, we can redefine as a new constant, C1. As we've been doing this in the past for separation. And so we're left with that this is actually just going to equal C1. E and the ln's cancel, so it just becomes t to the -1. Okay, so we got our W is equal to C1 t to the -1. And now we need to find V. So this means that we remember W is V prime. So V prime is equal to C1 t to the -1. Okay, so now I just need to take the integral of this. So what's the V if we know that this is our V prime? We'll take the antiderivative because we want to find V. What's the antiderivative of t to the -1? ln, right? So it's going to be C1 ln of t. Technically absolute value of t, but we're only looking for t greater than 0. So we could draw up the absolute value plus a C2. There's always an integration constant that comes out of that. So that's our V that we were trying to find. And so our solution form, this is our solution. We found the V that will force this to satisfy this differential equation. So our solution is now x of t is equal to V times sub t to the 4th. Our V is this thing. Times t to the 4th. Which if you multiply out would be C1 t to the 4 ln of t plus C2 t to the 4, which is exactly the same answer we had just said without justifying before, but this is your x1. I'll just move this down. This is our x1. This is our x2, where we have this additional factor of ln of t that got multiplied. But I don't say ahead of time that you had to multiply by this ln of t. Here, we showed that we would have had to, second homogeneous solution would have been multiplied by ln of t using this whole reduction of order. So we know one of the solution is for sure t to the 4 because we have r is equal to 4. Since it's a double, it's unclear what the other one is. And I just told you at the beginning of class that it's just going to be the same thing multiplied by ln of t. But this is the justification for why. What we do is we say we take the solution, homogeneous solution we're comfortable with, which is the t to the 4, multiplied by some function v of t, to be determined function v of t. We're going to determine that function v of t so that this is forced to satisfy the differential equation. You get an equation that's second order in v, but because of the fact that you can always show that your v terms will cancel, so all these purple terms will cancel if you did your product rule and derivatives correctly, your second order equation will never have a v term in it. It'll only have v double prime and v prime, but no v term. I mean, it could also not have a v prime term, but in general, it may have a v prime term. It will always have a v double prime term. So this kind of equation is quite nice because it doesn't have a v term. You can reduce the order of the differential equation by redefining defining a variable w to be v prime to get an equation that is, and you wouldn't be able to do that because if you had a v term here, because if w is v prime, then it's not clear. I mean, it's the antiderivative of v, but you don't even know what that is. So this reduction of order works simply because you don't have a v term in this equation anymore. Reduce it to a first order equation. A first order equation is quote unquote easier to solve because you just use all those methods we've learned, integrating factors, separation of variables. In this case, separation of variables, you get w, but w is v prime. But we're interested in v, so we'll take the integral of that. You're going to get an integration constant from finding w, taking the antiderivative of that will require, because it's a first order equation, you're going to get one integration constant for W. And then you take the antiderivative, that get your second one, and you need two because this is a second order differential equation, so you need two arbitrary constants. So that's the justification for why in the Euler equation, the repeated root case requires the second one to be the same t to the 4 like you had for the first solution, but multiplied by ln of t. So those are just justification, but the reduction of order is powerful enough that you can actually now not solve, you can now solve more kinds of equations, right? So this isn't an Euler equation because definitely this should have been t squared. So because this is not t squared, this is not an Euler equation. You can't use an indicial equation. It's and also unclear what, like, so indicial equation would be like, you know, a t squared minus, so what's b? B is kind of weird because you have like this is actually also violates the Euler equation because this 2t, by if it was just 2t, then it's okay. But this plus 1 is breaking the fact that this is, you have 2x, if you distribute this x prime to each of these, this equation technically has two x prime terms. And one of them is not being multiplied by t, but the other one is multiplied. So this is not an equidimensional equation. And also this violates Euler's because this should have been just a constant for this to be an Euler. You can't have a t here. So this is a non-constant differential equation that doesn't fall under this special case of Euler equation. So we don't know how to solve this. But reduction of order is a general method that allows you to take one homogeneous solution and build the full general solution. So if I mean, of course, you wouldn't know unless I told you, but if I were to hypothetically give you that, okay, this is my differential equation, I'm telling you ahead of time, one of the homogeneous solutions is e to the t. That's all you need for reduction of order. You just need one homogeneous solution. And then you have, you know, what do? You say, I propose. I got one of them, so I'm good to go because I can just say my general solution is going to be some v of t times this x1. In this case, it's e to the t. And I'm just going to let it rip, just kind of like take the derivative, second derivative, plug it in, and just kind of solve for the v of t that would have forced this thing. And you'll naturally get the second homogeneous solution and the full general solution from that. So, you know, you'll just say, okay, I'm going to just take the derivative of this. It's going to be x prime is equal to v prime plus v e to t. I'm just being very quick. You can check your check these derivatives. They're going to have an e to the t that's common for all the terms after you do product rule. And then there's terms that combine. So I'm just factoring out the e of t that would have been common when you took these derivatives, and then you plug it in. And you're just going to say, okay, but just keep in mind, this is your equation. So when you plug it in, it's a little more complicated because you have a t times all of this. Actually, I won't even put this parentheses, just use this. And then you're going to say minus 2, well, parentheses 2t plus 1 times this x prime term. And then plus the t plus 1 times this v of v times e to the t. Okay. And then this has to equal 0. And you're going to, I mean, I'm not going to have time to do this all, but the e of t's can get all, you can just divide everything by e to the t. And then I'll multiply everything out. And then, you know, what we're going to do is we're going to underline all the v terms in purple like I did before. We should notice all the v terms will cancel. In this problem, your v prime terms will not all cancel. Your v double prime, you'll get an equation kind of like this. It won't look like this though, but it'll be like something that's not that big after all the terms that cancel and combine. And then we're going to solve for that. We're going to reduce the order by setting w equal v prime, solve a first order equation in w, integrate that to get your v. And then your solution form will be your V times E of t. And so we'll do that next time. This is another equation that isn't Euler. So because there's a +1 here, and we'll do that as well. And then we'll look at having all of this with a non-zero right-hand side. And this is a different method for that. I do have 2 times that people can take the test today. I think one is right now at 1 o'clock, or yeah, at 1 o'clock, or right after in this room. And then there's one at 4 o'clock in 120, which is like the old room that we were in. And then there's a time for Wednesday. And then of course you guys could take it on Friday. So it's up to you when you want to take it.
When does the material for the test end?
Electrical circuits.
Okay,